Hi everyone, my name is Olivia and I'm a PhD student in the crop science group at ETH Zurich in Switzerland. And my talk is about estimating wheat head volume as a key yield determining trait. I'll talk about the background of the project and about the data collection, and then I will talk about how we estimate the wheat head volume. So let's start with the background. In the future, we expect higher or lower temperatures due to climate change, and this will lead to a different phenology in wheat. So one option to deal with this is to escape these stress events and to keep the sensitive phase in wheat, in the development of wheat, in a stress-free zone. A second approach, and our approach, would be to select for genotypes which are tolerant to heat and drought. So wheat yield is affected by the number of grains and the grain weight. But genetic gains in wheat have been more related to an increase in the number of grains than to an increase in the size of the grains. So the focus has been on the increase of the number of grains. And this leads us to the concept of the yield potential. I'll make an example here. We have two different genotypes, and one has many small wheat heads, and one has only a few but very large wheat heads. And they might have the same yield potential, that means the same volume, wheat head volume, that they can fill with grains. But in the end, the yield might be different because the spikelets inside, or florets inside the spikelets can still die. So to find out how efficient a genotype is under heat or drought, we need to estimate different yield components, such as the number of wheat heads, their volume, and the number of grains. But at the moment, there is no high throughput method to determine the wheat head volume. So what we did is we collected around 1,800 wheat heads, we tagged them in the field, we imaged them throughout the season, that means from flowering to harvest, and we harvested them at 3 different dates in a season, and we did this in 2 years. So after harvesting, we scanned the wheat heads in this 3D light scanner. We got the point clouds of the wheat heads, and then we removed the cone on the bottom that we used to fix the wheat head, and then we extracted the volume. So this is how we got the ground truth. We then also took 6 images per wheat head, 2 from a front view, 2 from a side view, and 2 from a mixture of both of them, because we wanted to collect as much information as possible. And then with these images and the measured ground truth volume, we wanted to train an algorithm or a model which is able to predict the wheat head volume. And now I will talk about the 2 different approaches that we used to estimate the wheat head volume. So first, we started with the easy baseline. We wanted to see if we can use the area of a wheat head to predict the volume. So we took the 6 images of a wheat head and segmented all the wheat heads. And when you do this, you get this nice mask that you can see on the right-hand side. Here we have zeros for the background and ones for the foreground, which is the wheat head. Then we detected the stalks at the bottom of the wheat head and removed them to make it a bit more accurate. And then you can sum up all the ones and take the mean of the 6 images. Here you can see the correlation between the true measured volume on the x-axis and the predicted volume on the y-axis based on the area of the wheat heads of the 6 images. We get a correlation of 92% and a mean absolute percentage error of 8.45. So the correlation looks quite nice, but then if you look at the larger wheat heads, you can see that our algorithm still over or underestimates their volume. So in the next step, we wanted to improve this correlation and use a different approach. So we use the same images as input of a neural network, which then predicts the volume of the wheat head as output. So on the left-hand side, you can see the results when we use 6 images per wheat head. We have a correlation of 96% and an error of 5.43%. And you can also see that now the correlation looks better for larger wheat heads. And then we were wondering if it already works when we only use 2 images, because this makes it much easier when you want to take images of the wheat heads in the field. So we made the predictions for 2 images. We used the front view and the side view, and here we get a correlation which is a bit lower, 93%, and an error of 7.47, but the correlation is still higher and the error lower compared to our baseline approach. Our next step was then to scale up everything and to use our field phenotyping platform, which has 13 cameras and that takes the images of the same wheat heads. The aim here is very similar. We want to use these FIP images that you can see on the right hand side. It's a bit more complex. We have different distances between camera and plant. We have to deal with occlusion, but still we want to use our ground truth to train a model that is able to predict the volume of the wheat heads. So first of all, we had to find the tagged wheat heads in the field images, and then we used them as input into these neural networks. And at the moment, we are able to achieve a correlation of 81% with these field images. So as a conclusion, the wheat head volume delivers valuable insight into stress responses, and predicting the volume on a very large scale in the field might deliver important information regarding genetic differences between genotype, heritability of the volume, and potential of different genotypes for the adaptation to climate change. Thank you very much for your attention.